All right, so let's pick up where we left off last time. All right, we sort of introduced these new reactions, these allylic bromination reactions that use this reagent NBS, N-bromosuccinimide. All right, and what we're doing is, as the name implies, we're brominating, substituting a hydrogen for a bromine in that allylic position, right? So if we look at an alkene here, those sp2 hybridized carbons about that double bond are what are called the vinylic position. But the one removed, the carbon one removed from that double bond is what's called the allylic position, and that is what gets brominated in this reaction. All right? You don't have to have this structure memorized, but we took a look at this structure of N-bromosuccinimide, and we noted that it had this very weak nitrogen-bromine bond, which is really just saying that it's very weak, so it breaks with this homolytic cleavage. So this NBS is a good source of these bromine radicals. All right, so this is another reaction that is going to go through a radical mechanism here. We'll talk a little bit more about products, but let's just address real quick why the allylic position specifically. All right. So first of all, what's important to note is that this is a substitution reaction, meaning that we're substituting that bromine on there and removing what? So what do I have more of over here than over here? Hydrogens, right? So over here there are 3 hydrogens in this allylic position. Over here, there's only 2, so I substituted out that hydrogen for a bromine in this reaction, all right? But why is it specifically that allylic position? All right, this one right here, this is our hydrogen that we're substituting, all right? Well, if we compare that to our vinyl hydrogen, our vinylic position, or just our sp3 hybridized carbon with its hydrogen, a normal old, not allylic position. All right, if we look on our chart here of bond dissociation energies, what we'll see is that allylic position is quite a bit weaker than those carbon-hydrogen bonds in those other positions. All right, so why the allylic position? Well, because the bond dissociation energy of this bond is around 440 kilojoules per mole. The bond dissociation, I don't remember, 460 kilojoules per mole. But this one is only 370 kilojoules per mole. So why the allylic position? Because that carbon-hydrogen bond is the weakest at that allylic position. Okay. Cool. So why is it the weakest at that allylic position? All right. So first of all, let's take a step back. We talked about allylic carbocations before. And these allylic carbocations are relatively stable compared to other carbocations. And why is that? When did we talk about the allylic carbocations? That was one of these patterns that we were taught to spy here. It was one of our resonance patterns, exactly. All right, so why is the allylic carbocation particularly stable? Because we have this resonance structure that we can draw. We can stabilize that positive charge by bouncing it back and forth between these 2 carbon atoms. All right, so our allylic carbocation was resonance stabilized. All right, and if we're instead talking about an allylic radical, So now instead of having a positive charge, I'm going to have an unpaired electron in that allylic position. We're going to be able to see the same thing. We're going to be able to resonance stabilize that unhappy unpaired electron. All right, so we can draw another resonance contributor here. Let me zoom in. Now we're showing the movement not of a pair of electrons. So notice here over with my carbocation, I used this double-headed arrow here. That's because I was showing the movement of this pair of electrons, both of those electrons. Remember, with radicals, we have to show the movement of a single electron. All right, so first of all, my other resonance contributor is going to have that radical and that double bond swap positions, just like we saw with our allylic carbocation. All right, the difference here is how I'm going to show the movement of those electrons. I have to use my fishhook arrows, right, because I'm showing the movement of individual electrons. Well, this electron is going to come down and form that new pi bond. Where's my second electron? It's going to be the one in this pi bond here, 1/2 of that pi bond. So then where does my free radical come from? The other electron in that pair jumps onto that carbon atom. And now I'm using my fishhook arrows, my single-headed arrows here, to show the movement of those individual electrons, movement of single electrons. All right, but nonetheless, just like a carbocation in the allylic position, our radical in the allylic position is resonance stabilized. Okay, so now let's try to predict some products of these allylic bromination reactions. Okay. Let's just say we're predicting products now. All right, so I'm going to put down an alkene. We're going to hit this thing with NBS. And I want everybody to take a second and brominate that allylic position. All right, carbon, 1, 2, 3, 4, 5. Which one am I going to brominate here? Right, my allylic position here is the one removed from that double bond, or carbon 3 in my numbering here. So let's go ahead and brominate that allylic position. All right, cool. So there's a little bit more to the story here. We're not going to do our full mechanism here, but we are going to discuss our intermediate. As we noted, this is going to be NBS is just a producer of bromine radicals. We are going to specifically choose the allylic position because that's the weakest carbon-hydrogen bond to break, and we're going to create this allylic radical. All right, so let's go ahead and look at we won't do our electron pushing arrows, but we are going to take a look at our intermediate here, which is that allylic free radical. All right, that free radical in that allylic position. All right, but as we discussed, what's stabilizing that free radical? The resonance. And so there's going to be another resonance structure that we can draw here. So everybody take a second based on what we were doing before. Draw my other resonance contributor here. All right, so my free radical, my free radical and 1/2 of that pi bond joined together to form my new pi bond. So now I have my radical has bounced over to the opposite end of that molecule. Okay, so my other resonance contributor, I have my radical and my double bond that have switched positions here. And whereas one of these allylic radicals would lead to the product that we drew, after this resonance occurs here, I would get a different product, which is when I brominate not that third carbon, but that very first carbon. All right, and so when we do this reaction with this alkene and hitting it with NBS here, we're going to get a mixture of these two products. All right, and to be clear, that first product, this is when I brominate my original allylic position. All right. And our second structure is what we get after that resonance of our free radical. All right, so we're not just going to get our, in this case, these are two distinct molecules, right? So after that resonance jump occurs, I get a radical in a completely different position, leading to a second product here. All right. Now this particular molecule, my substrate over here, had how many allylic positions to begin with? Just the one. All right. So now let's do our worst case scenario here. To be clear, these are both our intermediates. All right, but let's do another one here. All right, I'm going to treat this molecule with NBS. How many allylic positions does this molecule have? 2, right here and right here. And are they identical? No, right? Because I have this methyl group over here messing up my symmetry, these two methyl groups, messing up my symmetry in my molecule. So no, I would get a different product if I brominated this position than if I brominated this position. All right, so let's start with those two here. We're going to brominate one of those allylic carbons, get a mixture of this and this. All right, those were our original allylic positions, but now we're going to have other products after the resonance of our free radicals. So everybody take a second. There should be 2 new products that you can draw here. So everybody take a second and see if you can't figure out what those other 2 products are based on what we discussed previously. Oops. All right, one of them was arising from this free radical. The other one arising from this free radical. Now we got to do our resonance of these radicals to figure out what our other possible structures are. right, so now my free radical and my double bond have traded positions. So now my radical is down here on this carbon. All right, not only has my radical moved, but my double bond has also moved, leading me to this unique product. All right, and we can play the same game over here. Our radical and our double bond are going to swap positions here. So now my double bond's down here, and my radical is up here in this new position. All right, giving me again a unique product here. My double bond's in a different place, my bromine's in a different place, so this isn't the same molecule. So in this case, we would get a mixture of all four of these products here. Let me sort of simplify my coloring just so we can see clearly. All right, we've brominated those original allylic positions, right, with my double bond located in the same place it was in my substrate. But then because of resonance, our free radical and our double bond have now swapped positions, leading me to a distinct product. And if instead I start with my free radical from this product here, from this allylic position, again, do some resonance, my radical and my double bond have swapped positions. So we would get a mixture of all four of these products if we treated this particular molecule. This, what is that? 1, 2, 3, 4. 4,4-dimethyl cyclohexene with our NBS. All right, our allylic bromination reactions. Cool. All right, so this is how we can prepare our alkyl halides, specifically an alkyl bromide from an alkene, right? Putting a bromine on an alkene. We talked about our radical halogenation reactions, preparing alkyl halides from alkanes. All right, now we're going to move on and discuss preparing alkyl halides from alcohols. Okay, and we're going to have a slightly different technique for doing so, depending on our degree of substitution of our alcohols. So in the same way that we classified our carbons as primary, secondary, tertiary, we can do the same thing with alcohols. All right, a tertiary alcohol is when that hydroxyl group OH is on a tertiary carbon. So this is an example of a tertiary alcohol. To be clear, this carbon right here is a tertiary carbon because it has 1, 2, 3 carbon neighbors. We don't count our heteroatom when we're talking about classifications of a carbon. It's specifically the number of carbon neighbors, right? So this would be a tertiary carbon. So that's why this is a tertiary alcohol. That hydroxyl group is on that tertiary carbon. Okay, so tertiary alcohols are the easiest to convert into alkyl halides. You can do so very efficiently, very quickly, with just that hydrohalic acid. So hydrochloric acid, that would get you to an alkyl chloride. If instead you used hydrobromic acid, that would get you to an alkyl bromide. All right, presumably hydroiodic acid would get you to an alkyl iodide. These are by far the most common ones, HCl being the most common of the two. All right, and this is definitely a preferred method to do it because A, it's very efficient, very quick, right? Like literally mix these two things together, shake it up in 20 minutes, you got 100% yield of your alkyl halide product. The other thing is that in the grand scheme of reagents, hydrochloric acid, hydrobromic acid are about as cheap as they come, right? And this isn't something that we think about very much when we're doing pencil and paper organic chemistry. But of course, if you're running a lab, it's like running a business. You're very much so thinking about the cost of everything. So if you can do something really cheaply, that's the method that you're going to pick, right? So for tertiary alcohols, all you have to do is add in some hydrochloric or hydrobromic acid, and you will get an alkyl halide product. All right? We're going to note that for primary and secondary alcohols, this works, but not well. All right, so you can kind of force a primary or a secondary alcohol to become an alkyl halide using this method here, but you're going to get a low yield, takes forever, and requires heat. All right, which is never super desirable. The more heat that you impart on a substance, the more likely some side reaction that you don't want is going to occur. All right, so this works for primary, secondary alcohols, but it's not ideal. And what we're going to do is we're going to learn a different, more efficient method for primary alcohols. This is going to be our method for tertiary alcohols. And for tertiary alcohols, using this method, we're going to have a reaction mechanism. All right, so let's use hydrochloric acid here. And given that we've gotten so good at our reaction mechanisms here, I want everybody to take a second, and out of these two molecules here, you're going to identify what one's your nucleophile, what one's your electrophile. All right, see if you can't spy your nucleophile and electrophile, and then specifically your nucleophilic site and your electrophilic site. All right, hydrochloric acid, as the name implies, is an acid. And an acid, by definition, in order to be a proton donor, you need to be able to accept pairs of electrons. So by definition, acids are electrophiles. All right, and then specifically, what is the electrophilic site in this molecule? What is that electron poor atom? Our hydrogen. All right, this is our electrophilic site, which means that the chlorine is playing the role of what? Our leaving group, right? Our conjugate bases are leaving groups. Okay, cool. So my acid's my electrophile. I know that. If I'm going to look at this molecule here, this is then going to be my nucleophile, but specifically, what's my nucleophilic site? All right, so nucleophile is electron rich or electron poor? Electron rich, which is why they love those positively charged nuclei, right? What is my most electron rich atom in this molecule? Oxygen. And why? What's the giveaway of the oxygen? Those lone pairs, right? Nucleophiles have these lone pairs because they're going to donate those electrons to our electrophile. They're going to attack, kicking off that leaving group. All right. So then everybody take a second, following our electron pushing arrows here. What is my product of that first step in our mechanism? All right, so we have a bond breaking arrow here. So we've kicked off a chloride ion. And this was what? Bond formation, bond breaking, or both? What arrow is this? Bond formation. So let's create a new bond between oxygen and hydrogen. Get rid of my coloring here. And what else am I missing from this intermediate? That positive charge on that oxygen. It's got those 3 bonds. Remember back to our bonding patterns. Cool. All right, so this next step here is not one that you would necessarily intuitively know. All right. However, it does make sense because of our discussion of carbocations. It turns out that this thing here is now a good leaving group. All right, why is it a good leaving group? Because it will just leave as a neutral water molecule. Okay, but it just kind of falls off. All right, so there's nothing that kicks off that leaving group. There's no nucleophile that attack. It just kind of falls off of that tertiary carbon. All right, so why is that? Why would that just completely fall off our tertiary carbon? Well, if it falls off, what is my intermediate, my organic intermediate here? Carbon has how many bonds over here? 4, which it should, because that's how many bonds carbon likes to have. But then I'm going to steal this pair of electrons from it. I'm going to take this pair of electrons that was a bonding pair, and I'm going to make it a lone pair on my oxygen. So now how many pairs of electrons does this carbon have? Down to 3, right? So does it have a complete octet? No. Remember, that's our carbocations, those incomplete octets. All right? And so why does that water molecule, why does that leaving group just fall off? We form this carbocation here, but what do we know about tertiary carbocations? They're the most stable, right? So specifically for tertiary alcohols, we will get this mechanism here where we get a tertiary carbocation. All right, and that's because our tertiary carbocations are the most stable carbocations. All right, and what do we know about carbocations? Are they nucleophiles or electrophiles? They're electrophiles. They're really good at accepting electrons because they have an incomplete octet. All right, we got a water molecule that's neutral and this negatively charged chloride floating around. What's our good nucleophile going to be? All right, so when I'm looking here and trying to figure out which one's the better nucleophile, what should jump out to me as the most electron-rich here? The negative charge, right? So yes, that negatively charged chloride ion here will then attack that carbocation, leading us to our alkyl halide product here, specifically a tertiary alkyl halide. What's up? The water is certainly produced in this reaction, so if you were doing a balanced chemical equation, but we don't. You'll notice that we're always super lazy in organic chemistry, and we only ever really write what our organic product is. So yes, if I was going to be good, I would also say and water over here, but you will almost always see inorganic products omitted from your chemical equations in organic chemistry. We really only care what happens to our carbons. But yes, as our mechanism shows here, there is a water molecule that's produced. This would be called a dehydration of our alcohol, right? It's losing a water molecule, but yes. Okay, so then like I said, this is our preferred method for tertiary alcohols. Works really efficiently, quickly, don't need any heat. All right, for primary and secondary, you can kind of force it, but it's not ideal. So instead, we're going to have a different preferred method for primary and secondary alcohols. All right, let's look at them one by one here. For primary alcohols, okay, primary alcohols being when my oxygen, my hydroxyl group, is bonded to a primary carbon, one with only one carbon neighbor. All right, again, we're going to have a method for creating alkyl chlorides, substituting out that hydroxyl group for a chlorine, or alkyl bromides, substituting out that hydroxyl group for a bromine. But we're going to have to do some fancy reagents in order to do it, right? So now we're going to spend some money here on some efficient reagents. All right, the one that we would use for our alkyl chloride is what's called thianyl chloride, SOCl2. And in order to convert a primary alcohol into an alkyl bromide, we're going to use phosphorus tribromide, PBr3. Okay, so we got to use some fancy reagents here. We're not going to do a mechanism for this. This isn't one that I'm going to expect you to know. You can look it up. It is a well-known mechanism. It's not one that we don't know, but it is more than I feel like going into for this course. But suffice it to say that we can substitute out our hydroxyl group for a chlorine using thianyl chloride, or substitute our hydroxyl group for a bromine using phosphorus tribromide. All right. We're going to have the same techniques that we're going to be able to use, rather the same reagents that we're going to be able to use for a secondary alcohol. All right, but for secondary alcohols, there's another sort of complication that we can have. All right, unlike primary alcohols, is this carbon a stereocenter in my primary alcohol? No, and what's the giveaway? It's got two hydrogens, and by definition it has to in order to be a primary alcohol, right? This carbon can only have one carbon neighbor. Well, if I have a secondary alcohol, all of a sudden this can be a stereocenter, so I can have a stereospecific alcohol. All right, we can take a second to convince ourselves that if we labeled our priorities of our groups, this would be 1, 2, and 3. And since I'm going in the clockwise direction, that would make this specific stereoisomer the R stereoisomer. All right, so for secondary alcohols, we have this stereospecificity that we have to worry about. All right, if we start off with a stereospecific alcohol, and we do these same two reagents here, thianyl chloride and phosphorus tribromide, we will again substitute out that hydroxyl group for a chlorine. All right, but we're going to see a stereospecific product here. This is not a addition reaction like what we were seeing with alkenes. So we're not going to talk about syn or anti-additions. All right, these are substitution reactions. And for substitution reactions, we have a different type of stereospecificity that we're going to see, what's called a stereochemical inversion. Where if I start out with this R alcohol, I'm going to get an inversion of that stereocenter. So now my new bond here is not on a wedge like my substrate, but on a dash. All right, this is what's called a stereochemical inversion. My stereocenter went from being R to being the S stereocenter here. All right, and we see the same thing if we do our phosphorus tribromide. We have a stereochemical inversion, creating that alkyl bromide. Now, truthfully, this inversion happens in primary alcohols as well. We just don't have to worry about it. We'd never be able to see it because it's not a stereocenter. Right? Don't worry, we have no stereocenter. But if we have a secondary alcohol, all of a sudden we can have this stereocenter here, and this reaction is stereospecific, leading to a stereochemical inversion here. Our flipping of our wedged bond to our dashed bond. Right? So to be clear, our hydroxyl group was pointed out of the page at us. When that new chlorine bond forms, now it's pointed in the opposite direction. It's pointed into the page. Okay? Up here, we did not talk about stereochemistry at all here. All right? That's because I chose this alcohol that was not stereospecific. It had these 3 methyl groups on there, but I could just as easily have picked a stereospecific alcohol. All right, but in our mechanism here, we have a carbocation. So what does that mean in terms of our product here? What's the geometry of our carbon over here? Tetrahedral. And as soon as it loses that 4th bond, and it only has 3, what's its geometry? Trigonal planar. So those carbocations are flat, right? Which means that that chloride could attack from this side, or it could attack from the other side. Even if you started out with a stereospecific tertiary alcohol, you will always get a racemic mixture, which means that we don't have to worry about our stereochemistry, right? We don't represent racemic mixtures with our dashes and wedges. We can just use our straight line bonds. Okay, so for tertiary alcohols, we're not worried about it. We'll always get a racemic mixture. For primary alcohols, we're not worried about it because we don't have any stereocenters. But for secondary alcohols, we do have to be mindful of this potential for that stereochemical inversion, where if we start with a stereospecific secondary alcohol, we're going to get a stereospecific product, specifically with that inverted stereochemistry. Cool? Cool. All right, we got one more to go here. And this is a pretty cool one. This is what's called a Gilman reaction. All right, and the star of the show here in a Gilman reaction is a Gilman reagent. All right, and this is going to be our first reagent that we're going to see here, which is classified as an organometallic compound. All right, organometallic. What do we think the organo means? Organic. And what about metallic? Metal. So these are these weird compounds that have a carbon metal bond, which up until this point we've lied to you and told you doesn't exist, right? We don't talk about metals in organic chemistry. It turns out that there are special ones here that do form covalent bonds. So these are molecules where we have this alkyl chain, this organic half, bonded to a metal. And in the case of a Gilman reagent, that metal is copper lithium. All right, we're going to see a few organometallic reagents as we go through the course here. This will be our first one. A Gilman reagent specifically has copper and lithium as your metals that you're using. Okay, so what's so special about these organometallic compounds? Let's look on our periodic table real quick. All right, cool. Electronegativity, that's what we want to talk about. Let me get rid of all this crap. So normally, when we're talking about our non-metals, carbon is one that we don't consider to be very electronegative, right? Because we're always comparing it to nitrogen, oxygen, or our halogens, all of these very electronegative elements. But if we're going to compare carbon to copper, which one of those is going to be more electronegative? The carbon, right? In fact, metals do not hold on to their electrons very tightly at all. So in this bond here, very different from what we're used to seeing, we have a polar bond. Let me go back to where I was. We have a polar bond here, but it is the carbon that is hoarding all that electron density. Right? So my carbon now is the more electronegative element in this polar bond. My metal does not have a lot of electron density. All right, so what are so special about our organometallic compounds? We have a carbon hoarding a ton of electron density, which means it's what? A good electrophile or nucleophile? Nucleophile. All right, so our organometallic compounds here. We have a nucleophilic carbon. An element that we don't see playing the role of a nucleophile terribly often, right? But in these organometallic compounds, because we have this carbon-copper bond, and copper's not very electronegative at all, carbon is pulling that electron density, so it's going to be our nucleophilic site here. Cool. One thing to complicate things, I lied to you a little bit about what a Gilman reagent looks like. It turns out that there's actually two alkyl groups bonded to that copper, right? So we put it in parentheses with a little 2. Okay, we're going to note there are two alkyl groups bonded to copper, but only one will participate in the reaction. All right, now this particular Gilman reagent had how many carbons? This is a 3-carbon Gilman. It could be any size. All right, so I'm going to do an example with 3 carbons here, but if we're going to do our generic Gilman reagent here, it would just be R2CuLi, where R is anything. All right, so up until now, all of our reactions in this chapter have been about preparing alkyl halides. This will actually use an alkyl halide as a substrate. All right, so now let's look at we'll call this our predicting products. We're going to take an alkyl halide. We're going to treat it with our Gilman reagent. All right, so what's our reaction going to be? Well, as we noted here, our Gilman reagent is our nucleophile. And specifically, that nucleophilic site is that carbon that's bonded to our copper. All right. What do we know about alkyl halides? They like to play the role of what? Electrophiles. Electrophiles, yes. And what's our electrophilic site? Our carbon that's bonded to our halogen, because our halogen is what? Our leaving group. All right, so what do nucleophiles do to electrophiles? They attack. And so what we're going to have is a new bond between our nucleophilic carbon and our electrophilic carbon. All right, so we saw reactions where we were creating new carbon-carbon bonds in our alkyne chapter as well. Importantly, unlike our substitution reactions, I don't know, it's kind of easy to follow along when we're swapping out a hydroxyl group for a chlorine, right? It's kind of easy to see what our product should look like given our reactants. Here, whenever we're making new carbon-carbon bonds, our product is going to be bigger and uglier than our reactants that we start out with, right? So counting carbons is going to be very essential and making sure everything's linked up correctly. So what I'm going to do is I'm going to keep track of my electrophile carbons here in blue and my nucleophile carbons here in red. I'm going to start by redrawing that electrophilic carbon chain here. All right, and then I get to my electrophilic site, which again I highlighted in blue. So when I draw my new carbon-carbon bond here, what's going to be at the other end? It's got to be that nucleophilic site, right? That carbon that I highlighted in red there. And all three carbons from that Gilman are going to be joined on here. All right, so I'm going to make sure to include all three carbons. Okay, I have my electrophilic site and my nucleophilic site. I guess we can just say, here's our E site. Here's our N site. And we have this new carbon-carbon bond between our nucleophilic carbon and our electrophilic carbon. All right, and again, counting carbons is going to be important here. I colored them all so it's a little easier to follow, but nonetheless, my last double check that I'm always going to do is I have 1, 2, 3, 4, 5, 6 carbons on the left. I should have 1, 2, 3, 4, 5, 6 carbons on the right. Okay? Cool. So I want you all to try to do one on your own here. Okay. Sort of the nice thing about these Gilmans, there are a few reactions that we're going to learn where there's a bunch of rules as to what you can and cannot use as your substrate. For a Gilman reagent, there's very few restrictions on what will work. So for example, our halogen could be attached to an sp2 hybridized carbon, like in bromobenzene here. And this will work just as well. All right, so everybody take a second and try to predict my products here. All right, so I'm going to identify that nucleophilic carbon, again, the one bonded to my copper, bonded to my metal, and my electrophilic carbon, the one bonded to that halogen. All right, I'm going to start by redrawing that electrophile. And as soon as I draw my new bond here, what's going to be on the other side? My nucleophilic carbon. All right. Now in this case, my nucleophilic carbon here, I have this isobutyl group here, right? 4 carbons long with that little fork. So there's one of those carbons drawn. I got another one, and then that fork on the end, an isobutyl group. All right, and if I want to count carbons, I have 1, 2, 3, 4, 5, 6 from my electrophile. Those are easy enough to spy here in this benzene ring. And then I have my 1, 2, 3, 4, 1, 2, 3, 4 from my Gilman reagent. All right, so this, we can attach our halogen to sp3 hybridized carbon. So an alkyl halide, we can attach it to an sp2 hybridized carbon. We can even have an alkenyl halide, right? So where that is attached to a carbon-carbon triple bond. And that will work just as well. Specifically, if we have an alkene, though, we have this potential for a stereospecificity. All right, so this will specifically be for what are called alkenyl halides. Right, not alkyl, but alkenyl, because we have a carbon-carbon double bond. All right, and again, we got to worry about our stereospecificity. Because this is a specific stereoisomer of my alkene here. I have this ethyl group on the opposite side of this bromo group. So this would be what? E or Z? Are they on Z's same side? No. This one's on this side. This one's on the opposite side. So here's my E stereochemistry. All right, if I'm going to hit them with a Gilman reagent, just going to do a 2-carbon Gilman here. I'm going to have my new bond between my nucleophilic carbon and my electrophilic carbon. All right, but importantly, that new bond is going to be pointed on the same side as to where my halogen is. Right, so when I draw my new bond here, let me squeeze this in. On the other side, again, is that nucleophilic carbon. I'm going to make sure to add 2 of them since that nucleophile was this 2-carbon chain. All right, but our stereospecificity, kind of the best case scenario here, it preserves our stereochem. All right, so we're going to note our Gilman is added to the same side as that halogen bond. All right, so if this is pointed on the my halogen's pointed on the opposite side of my alkyl group, my Gilman's going to be added on the opposite side of that original alkyl group. All right, so if we have a alkenyl halide, we could have a stereospecific reagent here, and our Gilman reactions will preserve that stereochemistry. Cool. All right, that's pretty much it. Let's practice 2 more of these, and then we'll be done. Oh, here we go. Okay. Let me do an easy. Let's just do a regular old alkane first. All right, you'll notice that I'm always using bromines on these Gilman reagents. It turns out that alkyl chlorides, they don't work as well. And alkyl iodides are just more rare. They're more expensive. So bromine's a good in-between. Cool. Yeah, but you don't lose your double bond. I'll still retain that double bond in your quadrants. So it's going to be pointed in the exact same way on that program. So since your bromine is pointed up, your new bond's going to be pointed up as well. Yeah, so you keep your keyboard stickers. Oh yeah, cool. That's good. You're missing a carbon though. Oh, just compared to what I've drawn. I have 1, 2, 3, 4, 5 carbons in my gillet. So it's going to be pointed in the same direction as that bromine. So you have it as an E conformation where it starts out as a Z. So it's going to be a Z on the positive side as well. Right, that move on in the same direction as that bromine. Yeah, cool. Yep, exactly. Point it up, yep. All right, so what the heck did I do? Go back to where you were. Okay. I'm going to identify my nucleophilic carbon and my electrophilic carbon. I'm going to start by redrawing that electrophile. And then when I draw my new carbon-carbon bond, what must live on the other side is that nucleophilic carbon. All right, so if I'm going to keep track of my electrophile carbons in blue, that's these 5 here, 1, 2, 3, 4, 5. For my nucleophilic carbons, I got to include these 1, 2, 3, 4, 5. So this isopentyl group here, so here's one of them, 2, 3, 4, got that fork on the end, 5. All right, and always a good double check to count carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. All right. When I do this one here, I have an alkene. I'm going to identify again my nucleophilic carbon and my electrophilic carbon. But importantly, with these alkenes, I'm going to preserve my stereochemistry. So since these two groups are on the same side, when I do my product here, my new bond is also going to be pointed in that same direction. So now I'm going to point that bond up to my new nucleophile here, my nucleophilic carbon. That's 1. I again got to include those 5 carbons. So 1, 2, 3, 4. Got that fork on the end, 5. Okay, again, counting my carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got my stereochemistry preserved. These two groups are on the same side, just like in my reactant. And notice how we also keep our carbon-carbon double bond. This wasn't an addition reaction. We didn't lose our carbon-carbon double bonds. All right, we've retained our alkene in our product as well. Cool. All right.